So here's the plan for today. I heard we're in problem 8 of worksheet 14. So my plan is to finish worksheet 14 and then do worksheet 15, or at least parts of it. So today, finish. And then do okay. All right. So we stopped last time on problem 8, so we're in worksheet number 14. Problem 8. Problem 8. So on problem 8, you have the following. You have a capacitor and you have an inductor. So, and it says at t equal to 0, the magnitude of the current through the inductor in an ideal LC circuit is at its maximum value. So here is the capacitor, and here is the inductor. They tell me that this is positive, right? This is minus, right? At least that's what I see. And the current is going like this. That is the current. They give you several graphs, and they say which one corresponds. So they say the current is maximum and it's positive because it's going clockwise, right? So which graph shows something that is maximum? Either the solid or the dashed line at t equal to 0. Which one has a maximum? Which of the graphs? Let's go through them. Graph 1 or figure A or figure 1. Does it have either one, the dashed or the solid? Is any of them maximum at t equal to 0? No. How about figure 2? No. How about figure 3? Yes, which one? The solid, yes. How about figure 4? No. So what's by just the process of elimination, it's got to be which one? Figure 3. Okay. So figure 3 would correspond to the given information, right? And we know that, so the solid line would be the current, and the dashed line would be the charge, right? Would be the charge. So figure 3 would be the actual, would be the answer. So figure 3 would be the answer. So since this is an ideal LC circuit, we know the following. We know that the current, the charge as a function of time is usually given by the following: Q0 times the cosine of omega t plus some phase shift, and then the current I of t would be minus dq dt, so it's Q0 times omega times the sine of omega t plus the phase, right? Plus the phase. That's in general. Usually if the capacitor started being charged at t equal to 0, then the phase would be 0 and you just have the Q0 cosine of omega t with no phi. But here they're saying the current was maximum and the charge would be 0 at that time. So phi is not 0. But it has this form. Okay? It has this form. So let's go to part 2 of this problem. It says assume the units of the vertical axis are milliamps for the current and millicoulombs for the charge. And so the question is, what's the angular frequency? What's the angular frequency? So I'm going to do the following. Let's look at that figure. Let's please look at figure 3, which is the correct, right? Correct one. And we said the solid line is the current, right? The solid line is the current. So from figure 3, what is the maximum current? Let me see. From figure 3, I maximum is what? According to that. Huh? 2, right? Yeah, 2. You guys agree? Everyone? Are we on this together? Okay. So from figure 3, this is 2. 2 what? Milliamps, yes. 2 milliamps. Or 2 times 10 to the minus 3 amperes. Okay. Okay, good. Let's look at the charge, Q max. What is the maximum charge according to figure 3? So figure 3 would be the dashed line, right, for the charge. So what's the maximum charge? 1. So 1 what? Millicoulombs, right? They said, yeah, millicoulombs for the charge. So 1 times 10 to the minus 3 coulombs. Okay, so that's that. So now, how am I going to use this information to get the frequency of oscillations, or the angular frequency, this omega? This omega. Well, notice here, let's look at these two equations. What do you know? What's the maximum charge according to this equation? A cosine can only have values between what and what? Between +1 and -1, right? A cosine cannot exceed +1. So when the cosine is +1, what's the charge? Would be Q0. So the maximum charge you can have is actually Q0, right? So notice this maximum charge is Q0, right? And then what's the maximum current that you can have? Yeah, which one? According to this equation, what can the maximum current be? Q naught omega. Yeah, so the maximum current is Q naught times omega, right? Well, what happens if I divide I max over Q max? Look at this. I maximum over Q maximum. That will give me what? Q naught omega divided by Q naught, right? You cancel this and you just get omega, right? That's what this is saying. Telling me if I divide I max over Q max, I get omega. So let's use the numbers we have. I max is 2 times 10 to the minus 3. So 2 times 10 to the minus 3. And Q max is 1 times 10 to the minus 3. And that must equal to omega. So omega must equal to 2, right? Radians per second. 2 radians per second.
Can you explain again how cosine and sine go away? Where did we say the angles were?
Yeah, so we said, so this is the current as a function of time, right? And this is the charge as a function of time, right? So if you plot the charge as with respect to time, right? Charge on the y-axis, the time on the x-axis, you would see that this function would have a maximum value of Q naught.
Right.
So the maximum charge is actually Q naught.
Okay.
Yeah.
Oh, so yeah, that's what you were saying.
Yeah, and the maximum current is Q naught omega, because regardless of the sine and cosine they just oscillate between 1 and -1. Yeah.
Okay.
Yeah. Anybody has a question on this one? It's okay, going to continue? Not too bad, right? Okay, good. Let's see, how many do we have left? By the way, for people who just came in, we're just finishing worksheet 14 that we started last time, of course. If you don't have a copy of that, you can grab one. If you already kept yours from last time, you got yours from last time. So the next question is problem 9. And it says you have an LC circuit again. So problem 9, you got an LC circuit. And so problem 9. Problem 9. Here it is. You got an LC circuit, and then the capacitor is initially charged. Okay? The capacitor is initially charged. So you have this, a capacitor, and you have an inductor, and then you have this. So initially the capacitor is charged, and then you close the switch. So what happens when you close the switch? Let me open the switch first. So here's the switch. It's open. There is no current. The inductor doesn't have anything, right? So I'm going to close my switch, and here is the switch, closed. What happens now? This is capacitor, inductor. Charge starts to flow. Okay. It will start to flow, so it goes from the positive to the negative end, and there will be current, and then eventually this side will be positive and this side will be negative, and then it will turn back and over again. And it will oscillate according to these equations. Since the capacitor started charged, so the initial charge at t equal to 0 is q naught. So in this case, phi is 0. So for this part, for this case, you got this q naught. Q is equal to q naught times the cosine of omega times t, and the current is omega times q naught times the sine of omega times t. Right? That's the current and charge as a function of time. Again, where did the phi go? Why was I able to ignore it in this case? Using the initial conditions, right? The initial conditions tell me the charge at t equal to 0 is q naught, so it's maximum. So I conclude that if you plug in 0 here, you got cosine of phi. Since the charge is maximum, I conclude that phi must have been, the cosine of phi is 1. So phi must be 0, because cosine of 0 is 1. So that's it. Okay, so now initially, when the capacitor is charged, all the energy is in the capacitor. All the energy is in the capacitor, right? And it's in the form of an electric field. Okay? All the energy is in the capacitor in the form of an electric field. Does the inductor, initially, would the inductor have any energy?
No.
No. Because inductors have energy stored in their magnetic field, right? And their energy, if you like, is 1/2 Li squared. The energy in an inductor is 1/2 Li squared. The energy in the capacitor, remember, the energy in a capacitor, for a capacitor, is 1/2, since we have the charge and capacitance, so it's variable as q squared over 2c. Does anyone remember this one? 1/2 cv squared, q squared over 2c, or 1/2 cv, I'm sorry, 1/2 qv. So that's the energy in an inductor. Anyone remember that one?
1/2 Li squared.
1/2 L I squared. Thank you. L is the inductance, and I is the current. Good. So what happens is, when the capacitor discharges, how much charge will it have? Eventually, how much charge? 0. So the energy in the capacitor in that moment would be 0, right? But energy is conserved. Where did it go? You got a current now going on. So the energy is stored in the magnetic field, or in the current here. Well, it's the current running, so therefore there is a magnetic field in the inductor, and so that is your energy. So it oscillates between these two, but the sum, the total energy, has to always be constant. Okay? Has to always be constant. Why? Well, if energy is conserved, it means conserved means stays constant, right? Over time. It doesn't change over time. So let us look here. Let's look here at the options that they give us. Do you think A is true or false? Okay. So look at the energy. It's q squared over 2c, right?
Yeah.
Let me plot q for you as a function of time, and then square. So here's q. Here's q as a function of time. Here's t, time, and here's q, right? And so the charge starts here. This is 1/4 of a period, half a period, 3/4 of a period. This is a full period, right? Okay. That's the charge. But energy is charge squared, right? It goes like charge squared. So let's square. So if I do, here's t. If I plot the charge squared, or 1/2, or q squared over 2c, let's say this is q squared over 2c. It's the same function, but you just square the Q and divide by a constant. So what happens when you square it? Well, let's put the, well, what happens to a 0 when you square it?
0.
It's still a 0. So at this point and this point will remain the same, right? And now this one, when you square it, what does it become? It becomes more positive, right? It stays positive. If it's positive, it will stay positive. So it still has this shape. Now, how about this negative? When you square it, what happens? It becomes like this, right? Yeah. And this one stays positive. So something like that. That's the of sine squared or cosine squared. So how often do you get the maximum Q squared per period? You got it twice per period, right? Well, if you start here, and that's here. And then here, so you start counting again for the next period. So you get it twice per period. So the energy is maximum actually twice per period. So twice the frequency. So the frequency at which the energy stored in the capacitor oscillates is twice the frequency. It's twice the omega. Because it happens at twice every period. So it's true, yeah. Part A is true. So A is true. How about B? I think we said this, but let's see if you're. Yeah, B is true. So it says the sum of the two curves in the graph must be constant because energy is conserved. Yeah. Okay. The other one says the sum of the two curves must be constant because the curve is proportional. One is proportional to sine squared, the other is proportional to cosine squared. What do you think? Well, we have to inspect it, right? It turns out to be true. C is also true. I will get back to C in a moment. So C is true. How about D? I will go back to C in a moment. How about D?
Yeah.
D is true. It says the energy or the storage of energy in the magnetic field is out of phase with the storage of energy in the electric field. That's true. Because they can't be in phase. They cannot be both maximum at the same time. Or both minimum at the same time, right? Because if both are minimum, meaning 0, well, where did the energy go? Then you don't have any energy. It just disappeared. So when one of them is max, the other one has to be 0, and they keep alternating. That's why the curves look out of phase. It's good. And then, so D is true. So A, B, C, D are true. E turns out to be incorrect. So let me convince you why C is correct. The sine squared plus cosine squared has to be true. So here is why. I'm going to use this equation, these two, and show you why the energy will be conserved. Okay? Everyone with me? I'm going to use these two. So I'm saying this, the energy in the capacitor plus the energy in the inductor, when I add them, it's constant at all times. And it's a simple trig application. So let's start with this one. So the total energy will be 1 over 2c times q squared plus 1/2 of L times the current squared, right? The capacitor energy plus the inductor energy. That's it. You get 1 over 2c times q squared, right? But what is q? It's this. Q naught cosine squared. So you got q naught cosine of omega t, the whole thing squared, and then plus this one, 1/2 L, and then I squared. But I is q naught omega sine of omega t squared, like so. So now let's square them. When you square it, you get q naught over 2, q naught squared over 2c, and then cosine squared of omega t, plus 1/2 of L, and then q naught squared, and then omega squared, thank you, and then sine squared of omega t. But what do we know about omega for an LC circuit? What is omega? How is it related to L and C?
It's,
1 square root LC.
1 over the square root of LC, thank you. So omega squared is actually just 1 over LC. So I have an omega squared there, I'm going to replace it by 1 over LC. So this omega squared will be replaced by 1 over LC. Let's see what we get. Q naught squared over 2C cosine squared of omega t plus 1/2 of L Q naught squared, and then 1 over LC, for this omega squared became 1 over LC, and then sine squared of omega times t. Notice L and L cancel, and this becomes Q naught squared over 2C. Q naught squared over 2C. So both terms. So factor the Q naught squared over 2C. And that gives you cosine squared of omega t plus the sine squared of omega t. And what is sine squared plus cosine squared? 1, regardless of the time. So you just get Q naught squared over 2C, and that's a constant. As expected. So that is constant. You encountered this last semester, or something similar. Does anybody remember when?
It, kinetic energy.
And potential energy for a mass spring system. Yeah. When the spring is stretched, the mass has 0 kinetic energy but maximum potential energy in the spring. When the mass goes through the equilibrium, it's moving fastest, but the spring is not stretched, not compressed. So it has minimum. It has 0 potential, maximum kinetic energy. So yeah, we have seen this, and it actually works exactly the same way, the sine squared plus cosine squared. Okay. So E is not correct because if you plug in the numbers, it turns out not correct. If you want, I can explain it later during the break. But you should verify it on your own. Just plug in the numbers that they give you. Okay. Let's see. So we finished 9. I want to move on to 10. Problem 10. And so problem 10, yeah, is, I almost said it's the last problem in this worksheet, but it's not quite the last problem.
second to last.
Second to last, yes. So let's move the camera there. And so for problem 10, how am I doing? Problem 10. We have a capacitor initially charged with a charge Q naught. This is the capacitor C. This is the resistance for a resistor. And we have our inductor. And then we have our switch. This is the switch. Now you close the switch, what happens? Current starts to flow. Right? Starts from 0 and builds up. And the question was, so the first question, what's the relationship between dq dt and the current? So let's close the switch. So for part 1, I know the current is always dq dt, but either plus or minus, one of them. I know the current will flow this way, so that's the positive direction, right? But what's happening to the charge? Is it increasing or decreasing? Decreasing. So dq dt itself is a negative quantity, right? dq dt is a negative quantity. So if I want my current to actually be positive, what should I do? Huh? So I know the current will go this way.
Wait for the inductor to be charged.
I don't want to wait. I want to right away put something. I want to write an equation. Yeah. I mean, yeah, you can wait for the inductor, it will eventually switch sides. But let's say, initially, when the current is going like this,
So let's do it the other way.
huh?
Make your current, you make it go, counterclockwise.
Counterclockwise is positive,
Yeah.
but I know the current will go this way. Right? Initially, when you close the switch, the current is the direction of the pluses. The pluses will flow down.
But isn't that negative? It's negative dq dt.
So I want it to be positive. So how do I do that? Yes. Make it a minus. Yes. So now it's positive. Yes. Yes.
Oh.
I think maybe
Sorry.
we're explaining it like
Yes,
that.
it is actually that simple. So dq dt is a negative quantity because the charge on the, when I say the charge is decreasing, I mean the charge on the top plate here. In it, when you close the switch, it will start to decrease. But for sure, the current will go this way. It can't go this way because if it goes this way, then the charge is increasing, and it's not. Yeah, so that is the, minus dq dt. That is the current. What am I? So the next one, it says, use the loop rule to write an equation. So let's use the loop rule to write an equation. And I emphasize, right, the loop rule comes from, you got Faraday's law. Technically, it's, you're using Faraday's law, but we're, loosely speaking, here's what we're doing. Part 2, we're going around this, right? We're saying when you go across a capacitor, what's the change in potential? When you go from the minus plate to the plus?
Positive q over c.
Yep, it's did they use capital Q or, yeah, they use capital Q, so it becomes positive Q over C, right? Okay, good. Now, the current is going this way, so when you go in the direction of the current and cross a resistor, what's the change?
Minus
Minus IR, thank you. And then when you go in the direction of current and go across or through an inductor, minus L di dt, thank you. And then equal to 0, right? Yeah. Yeah. So that's that. I think that's all they want for this one, right? So what's the option? Which one?
B.
B, right? Yeah, B is correct. What's the next one? It says, replace your expression for the current that you picked in part A into the equation to get an equation just in terms of Q, right? Okay. So what can we say? I mean, I have the current is minus dq dt. So what is di dt?
Negative, the second derivative, d squared.
Thank you. Yeah, dt squared. So for part 3, this becomes a plus, right? Because there is a minus, and then the di dt itself is negative dq dt. So you will get Q over C minus IR plus L times the second derivative of Q with respect to the time equals to 0. They probably would organize it from the highest derivative to the lowest. Oh, I forget. And then the current here, we need to replace it by a
Or dq dt.
yeah, by a dq dt, sorry. So, the current is minus dq dt, right?
Yeah.
So negative current would be positive dq dt. So let's do it here also. Let me write it as L, second derivative of Q with respect to the time. And then here it becomes plus R and then dq dt. And then you got Q over C. I think I have it right now. So which one is the correct answer?
B.
D, right? D. Okay, good. Okay, so D is correct. Problem 11 is actually related to this. It's basically like it, but they want you to recall what you did in, remember when you had a block attached to a string and it oscillates, right? Physics 130.
Professor, I don't want to remember.
Yes. So it oscillates, and if there is friction, does it oscillate forever or eventually stop? It will stop because there is damping. See, when we had, remember earlier when we just had the capacitor and the inductor? We didn't have the resistor, right? This part was 0 when we didn't have the resistor. So it oscillated forever. But now there is the resistor, which resembles basically the friction. Resembles the friction. So here is a mass spring system. Mass spring system, just checking the time. So for problem 11, so you got, let's say your spring is stretched, right? Yeah, so I mean, let's say the velocity is this. That's the velocity. In what direction is the force of friction? Yeah, to the left, right? Because friction, if you move right, what does it do? Opposite. And then the force of the spring is in what direction?
Left.
To the left also. And so let's say the force of the spring is negative, and the friction is negative to the left. And then, so let me write it this way. The force of the spring is minus kx, right? This is the magnitude, kx, and then the minus is, let's say, the direction. And then the force of friction is, they say it's proportional to the velocity, so b times v, right?
Wait, I didn't get. Oh, it's B there.
B is technically, if it's the friction, B will be mu times the normal force divided by the magnitude of the velocity.
It's the constant.
It's a constant, yeah, B is a constant. Yeah, so B is a constant. And then you got the mass times acceleration, right? The net force equals to ma. So, yeah, net force equals to the mass times acceleration. So if you move everything to one side, mass times acceleration, what's the acceleration in terms of velocity? It's dv dt, and therefore it's the second derivative of x with respect to time, right? Yeah. dv dt and v is dv dx dt. Move this to the other side, you get plus b times v, but that's dx dt, right? And then this one plus kx. Which one corresponds to this?
B.
B, right? Yeah, B.
B and D the same.
Yeah.
Oh, yeah. Yeah, I guess either B or D. Yeah, why?
Oh, yeah.
Right, yeah, I made a mistake. Maybe I had another minus sign somewhere. Anyways, so yeah, so that's the right answer. Okay. And so they say compare these. Let's compare this equation and this equation. So, and let's think about it. The resistor plays the role of the drag force. Do you agree? Yes. So A is correct. For part 2, the resistor plays the role of the drag force. The current plays the role of the velocity. Yeah? Yes, the current is like dq dt, the velocity is dx dt. Let's see, the inductance is like 1 over k. Where is the inductance? It's with the second derivative of q, right? So it's similar to the mass, actually. Inductance is like resistance to changes. The mass, the heavier it is, the more resistance to changes in velocities, right? So A is right, B is correct, C is not correct, right? L is equivalent to M. And they say here the electrical energy in the capacitor is equivalent to the potential energy in the spring. So think about it. What do you do to get this thing moving? You pull it, that's potential energy in the spring, and then you let go, right? what do you do to this circuit to get the current going? You charge your capacitor first, and then you let it go. You close the switch. So yes, so D is correct also. D is correct.